Hi there, welcome to our channel where we talk about traffic operations in practice. The overall intent of this video series is to reduce the learning curve for students and entry-level engineers by providing them free and high-quality learning materials in the field of traffic operations, including highway safety and travel demand modeling. The majority of content in this work is written by Professor Jiangling. My name is Amit Kumar Singh. I'm one of the contributor of this work. I'm a licensed engineer in the state of Texas. I received my bachelor's from IIT Bombay in India and my master's from UT Austin in US. Other three contributors of this work are Priyanshu Singh, who works in the field of artificial intelligence, Nidhi Kumari, who has a background in computer science and is a programmer, and Namrata Kumari. She has a background in electrical engineering and currently she is working as data scientist. Now let's get to the main content. In the last video, we looked at the theoretical side of trip generation, which is the step 1 of 4-step travel demand model. We will look at the practical side of trip generation in future videos. In this video, we will focus on step 2, which is trip distribution from the theoretical side of things. Again, we will look at how these concepts are implemented in practice and how they are used in future videos. So right now we are only trying to cover the theoretical or academic side of things. So the second step is trip distribution. So first we look at what is trip distribution. So the trip generated from each zone calculated in step 1, which we looked at in the last video, are distributed to all other zones. This is called trip distribution. So let's say we have zone 1 here, then we have multiple zones in the study area. Let's say this is zone 5, this is zone 7, and this is zone, let's say, 11. So in step 1, we tried to figure out how many trips will be exiting from zone 1, let's say 100, and how many trips will be entering in zone 1. Let's say we are looking at daily traffic and not hourly. Hourly is a different kind of scenario. So let's look at in one day number of trips exiting is 100, number of trips entering is also 100. Now we need to figure out where these 100 vehicles will go, whether we'll go to zone 5 or go to zone 7 or go to zone 11, or they will go to all three places and in what proportion. So that's all trip distribution step is all about. So in last video we kind of ended at something called PA, production attraction table, that gives us number of trips that are produced and attracted for each zone for each trip purpose. So what we have is zone number here, we have production, we have attraction, and we have bunch of zone numbers. If this is a daily production attraction table, then most likely we will have equal numbers of production and attraction, assuming that people who leave their house for certain reasons come back. So they are almost equal. However, this they do not need to be equal if we are looking at uh, hourly distribution. Another thing about PA table is generated for each trip purpose. So let's say we are looking at a PA table for home-based work. Then there will be a separate PA table for home-based non-work, and so on. There will be another PA table for education, and so on. So the output of this step is origin destination matrix. So what we'll try to do is take this PA table. Another point to consider here is when we sum up the total production and total attraction in a closed system, they need to be equal. So let's say in previous step we calculated total number of production to be 5,000 and total number of attraction to be 4,500. Then what we can do is either reduce this number to become 4,500 or bump up this number to become 5,000. So we can change one or all of the elements to make this 5000, or we can change this 4500 to match 5000. But overall productions, total production is equal to total attraction. So we will look at how we do this in practice. This is called PA balancing, or balancing the production attraction. So we will look at how we do balance this out, but for simplicity, let's assume that total production and total attractions are balanced and they are equal. So let's say this is our PA table. This is zone, this is production, attraction, and these are some data points. Let's say we have zone 1, zone 2, which goes up to zone N, and production is given by P1, P2, and Pn. Attraction is given by A1, A2, and An. And we are trying to convert it into equivalent OD table in this step. So it's in trip distribution step. So we are trying to define OD table. Origins are defined in vertical column. So 1, 2, 3, these are my origins, and destinations are defined in the rows. So 1, 2, 3 up to N. These are my destinations, and these are my uh, origins. So let's say I'm looking at one of the numbers. So T32. What this T32 is representing is total number of trips that is going from zone 3 to zone 2. That's what it means. So here we have a different number of trips. The important thing about this table is the sum of all the numbers in the column needs to be equal to the total attraction, and the sum of all the numbers in a row needs to be equal to production. Because if you think about it, T11 is total number produced at zone 1 going to zone 1. Trip 12 is total number of vehicles generated at zone 1 going to zone 2, then generated at zone 1, zone 3, zone 1, zone N. So if you sum it up, it needs to equal to total number of trips generated. Similarly, total number of trips attracted. And when we sum it up, total number of trip generated and attracted needs to be equal uh, by the property of balanced PA table. Before jumping into how this table or this matrix is determined, let's look at one very important characteristics of this matrix, which is given in this paragraph. So this is a very important paragraph for not only for trip distribution, but for many kind of mathematical equations we come up with in practice. So it's not only relevant for OD trip table. There are other related applications of what we are going to discuss. So we usually don't work with mathematical equations. We usually work with matrices. So we have some matrices. We are trying to estimate some other matrices in practice. So it's related to that. What this paragraph says is we are trying to find all these variables. So the number of variables in this matrix is n square, such that the sum of horizontal rows, this is the information we have. We have pi, we have ai. That's all information we have. So we have p1, a1, p2, a2. So the known values are given in this last row and last column. So the number of known values is equal to 2n. So n numbers in this column, n numbers in this row. That's all we know. We know 2n data values, and we are trying to predict n square numbers such that these 2n values are kind of matched. So if we think mathematically, what we have is t11 plus t12 plus so on. T1n needs to be equal to p1. This is one equation. And similarly, we have two n equations. So we can write total equations. So one for each row and one for each column. And total number of equation will be 2n. So we have two n equations and n square unknowns. So whenever we have uh, more variables than the equations, so whenever n square is greater than 2n, uh, this is true when we have more than two zones, which is, uh, happens every time. Usually we have more than 1,000 zones. So whenever n is greater than 2, what happens is we will have more given that n is a positive number, we will have more uh, variables than more known or more equations. So we have more variables than equations. So what does it mean in simple terms is, let's say I'm writing an equation x plus y is equal to 10. This equation we know from high school is a linear line. Now there can be many solutions to this. There is only one equation and two variables here. If we have more variables than equation, what we can do is we can choose any one of them. Let's say I chose my x to be 1, then my y will become 9. Let's say I chose my x to be 2, then y will become 8. So there are infinite solutions to a set of equations whenever the number of variables are greater than number of equations, because we can still uh, number of the number of variables are greater than a number of equations, and these equations are linear equations. So what we can do is we can still use 2n variables to calculate the equation, and we have the leftover variables where we can choose anything we like. So what happens is OD trip table for most practical purposes is an underdetermined system, and as a result there are infinite set of ODs that can yield back PA table. That's a very big statement and very something to absorb. It's a simple mathematics, very simple mathematics with little bit of thinking. It's not really difficult. But what it says is there are infinite set of OD matrices that can be fit into trip generated. So in step 1 we came up with a PA table. Now we are trying to distribute it to generate OD table. And what this statement says is there are infinite set of OD tables that will match that PA table, and so on. This is infinity. So now the next question arises is, if we have infinite set of OD tables which can generate PA table, how do we go and choose which one should we use for practice? And that's where there are different methods to choose which OD table to use, and based on which method we are using, we will end up with a different OD table. So the OD table is not unique. OD table depends on which method, what priorities we are using, and what procedure we are using. So whenever a OD table is given to us, the first question we should ask is how it was generated, what method was used to generate that OD table, because there are infinite set of OD tables that can satisfy a certain PA matrix. Now the next factor talks about base OD. So we work on travel demand models to predict future traffic pattern. So usually what we have is some existing data, let's call it existing. What we have is existing count data and a little bit of existing trip pattern. What we use travel demand model is, or what we are trying to do is, what we have is future socio-economic factor or TAZs. So we have future, this is our future, let's say 2050 or 2045. Let's say we have TAZs and socio-economic factor with TAZs. Let's say we have a roadway network with all the proposed improvements. Let's say there is a new high-speed train. There are many things that in the roadway network that are given to us. So we have the transportation infrastructure known from the future, and we have the TAGs and all the variables estimated for the future. What we are trying to do here is trying to see how many trips are generated, where they will go, what route they will take, and that's what we are using travel demand model for. So what second this paragraph introduces is something called base metrics. So let's say this is my existing network, and let's say this is my future network. So this is my existing network, this is my future network, and let's say this is a roadway network, this is my future roadway network with more roads and kind of more complications, and there are some developments here in existing, whereas in future there are developments everywhere. Let's assume. So in existing, there will be some vehicles will go from here to here, here to here, here to here, here to here, but there will be only few vehicles going outside because there isn't much development outside here. However, in future, the city has expanded and now there will be trips from this location to this location, this location to this location to this. So what it means is the future OD pattern will be different than existing OD pattern, which is kind of intuitive. If we look in future, people are not going to make the same trips. If there are people going from one community to downtown, people may be going from one location, one particular zone to a different side of city in future. So what we can collect in existing is called existing OD, and what we are trying in this trip distribution step is to figure out future OD. Future OD. So there is a concept called base OD matrix. Base OD matrix is an equivalent OD matrix from the future. Let's say I have this future matrix, and what base OD matrix is an estimation of future OD matrix. So a base OD matrix is an OD matrix that hypothetically represent the future OD matrix because future OD matrix is unknown. So let's say we did this adjustment and we try to figure out some pattern, and we figure out the pattern but not the actual number, then those pattern is called base OD matrix. That's what base OD matrix is. Base OD matrix may be similar to existing or may be vastly different than existing. So we use the existing OD matrix and this future land patterns to figure out base OD matrix and then future OD matrix. So let's say we have a knowledge of base OD matrix from through some estimation. So the existing OD matrix is used to develop base OD matrix because assuming that not a lot of things will change, and adjusting existing OD matrix along with the future land plan to come up with base OD matrix. The next paragraph discusses the limitations of these OD matrices. So why we are developing base OD matrix when we can directly develop future OD matrix is kind of is described here. So in practice, generating existing OD data from all zones to all zones is nearly impossible. So the first thing is the existing data collection. There are various ways of collecting data. Those are listed here, such as OD survey, license plate method, GPS tracking, Bluetooth data, etc. Those can generate OD data. However, usually most of the studies only generate a sample of data, or let's say Bluetooth tracking. They are only located along the major roadways, or there are some intermediate points where we cannot track where those vehicles are going. So existing OD pattern is not completely collectible. So generating existing OD data from all data sources are nearly impossible. So the reliability of OD data depends on the data collection techniques, percentage of actual trips collected in the sample data, and the data quality. Most OD data are based on only a fraction of total trips, leading to poor base OD data. So what we have is not the actual existing OD matrix, we have an estimated existing OD matrix, which we try to take it forward for future and call it base matrix using some adjustment. So this is a count. So this is my existing OD based on count, and then there will be some OD which will come from travel demand model. So this is my count, and there will be OD that will be generated by travel demand model. Both of them combined together is used to generate existing base matrix. Existing base matrix. What existing base matrix is taking a distorted OD count from existing, is taking a distorted OD matrix from TDM, because TDM is never accurate in some sense. TDM ODs are, is generated based on certain assumptions, so they are hardly reliable. So what we are trying to do is taking one distorted OD from here, one distorted OD from here, and try to combine them together to become a kind of reasonable but still distorted existing base matrix. And then we will use the future TAZs and other factors on the base ODs to predict the future. So in future years, several changes in transportation network population demographics can significantly change the future OD matrix from existing OD. Consequently, estimating the base OD matrix for future is challenging. So one of the reason for future matrix estimation of existing base matrix to be challenging is there is no way of directly collecting future OD matrix. We cannot go in 2050 if we are in 2022 to go and collect the OD matrix from future. The assumption that existing OD matrix will be similar to future OD matrix is a significant assumption. So all we have in travel demand model is existing OD matrix, and then there are infinite set of OD matrices that are coming from TDM. So what we are trying to do is we are trying to pick one of these ODs such that the future travel patterns are kind of matched and existing OD is kind of matched, because predicting the future travel pattern is kind of difficult, and then we are trying to use existing OD to uh, supplement the future OD estimation. So again, we started with trip generation, then we came up with infinite set of OD solutions that satisfy this PA table. Now we are trying to pick out of this infinite set of solutions, which one should we be picking. So one way of picking some of the solutions is we pick a future OD that kind of looks like existing, and we can pick the OD that kind of looks like what we are supposed to generate based on future travel patterns, future land use developments, and roadway network. So one OD comes from figuring out future land use developments and future uh, a roadway network, and one OD comes from existing kind of counts, and both of them combined together we developed a kind of equivalent OD called base OD before we use those base OD to generate future OD metrics. And manually adjusting existing OD to account for all future changes is practically impossible. So what we do is, hence it's very difficult to obtain a reliable base OD matrix which we are going to use for future. In most cases, existing OD matrix is typically used as base OD matrix. Uh, Proper care should be taken before using any base OD matrix for future trip distribution. If a base matrix is used, then engineers should ensure that data and assumption behind the development of base matrices are accurate. So again, the data we collect from OD in the field using different methods here, which are listed here: OD survey, license plate, GPS, base data, Bluetooth tracking, etc. Those have limitations. Either the sample size is small, or we are only covering some major roads, or or the data quality is not good. So the existing OD is kind of distorted. Then we are trying to figure out future OD, but we do not have all the information. So we are trying to combine the existing with what future will look like to come up with a base OD. And since base OD development is complicated, we should be careful about how the base OD is developed and how is it applied for the future. So two different approaches are used for future trip distribution. First one is growth factor method. So growth factor method is used and is reliable if the base OD matrix is available. So if we somehow are able to generate base OD matrix, we will generate base OD matrix which combines the existing counts and future pattern a little bit. Then we will use the growth factor method. And if a reliable base OD is not available, then uh, gravity model is used. In practice, at least for the models I have seen, we go with gravity model. We do not even jump into looking at base OD. So figuring out base OD is very tricky. Again, is kind of nightmare is to work with existing incorrect OD, existing OD, which comes from different sources and they are hardly correct, and then playing around with estimated future OD to come up with base OD. So future OD is not actually the future OD, it's like a crude estimation of future OD to come up with base OD. So typically this process is very subjective and it's not practical to go ahead and adjust things to come up with future OD. So typically we do not come up with a reliable base OD and we switch to gravity model. Gravity model does not require any base OD. It actually does not require even the existing OD. It just takes the future trip patterns. You just look at what is happening in the future and estimates from where trip will go, irrespective of how the existing trip pattern is. So gravity model is kind of skipping some of the steps. There are some limitations to gravity models too. One of the biggest one would be, since you are not counting for existing and you're completely relying on zone patterns, if the models are not that accurate and not all the decisions are made based on formulas in gravity model, then we will not be generating a correct OD pattern. So we will look at two different methods to choose which which is the final OD pattern. So again, what we had at the beginning of this step is PA table, and what we end up with a infinite set of origin destination solutions, and what we are trying to do is figure out which one to pick. Now since there are infinite solutions, there are different ways we can pick it. One is to develop something called base OD and use something called growth factor method, which we are going to discuss next. Another one is just to look at the future TAZ, land use and roadway and estimated trip pattern. So let's call it land use and roadway, and do not look at existing pattern at all. Then that will become gravity model. For simplicity, the travel demand models I have seen are typically built on gravity model. There are some advantage of going through growth factor method such that we can account for existing data and existing count. There are advantages and disadvantages of both. So we will discuss about it next.